Hello guys, welcome to another amazing maths tutorial. This tutorial we're going to get deeper inside jit.gl.pix and we are going to render some sort of sun-like shape which I was experimenting with, and I want to share with you what I've discovered. So first of all, I've created my QMetro, the jit.gl render. Let's call it not sun but tut04. And I also added a jit FPS GUI object so we can see our FPS rate. Then let's create our jit window, call this tut04. Let's give it the attribute sync0, the floating one attribute, and the size is let's make this 500 by 500. Here it is. That's too small. Let's make this 600 by 600. Alright, so let's create our jit.gl.pix object. Let's call it tut04. Let's create our matrix. 4 planes, float 32. Let's make this 600 by 600. Let's touch the bang here. Plug this matrix into the jit.gl.pix, so we are feeding it with this 600 by 600 matrix. This will give us 600 pixel window. And then we need the jit.gl video plane object. Let's with the name tut04, the attribute transformers at 2. Alright. So I hope you remember something from the last tutorial, because we are going to use a lot of the functions we saw in the last tutorial. So first of all, let's delete all this stuff. And let's create our snorm object, which gives us our normalized signal coordinates. And we have to get the dot product of this. Actually, this is a vector going from the center of the axis to every point in the axis range. So the dot product, if you don't know what it is a product from two vectors. So if we do the dot product, which is this dot, it's represented by a dot, and these are two vectors, A and B, and we get a number. This is just a scalar number. It's not a vector. So what it really does? It does the product, so the regular product from the first component of the first vector with the first component of the second vector, and then adds this to the product of the second component of the first vector with the second component of the second vector, and this goes on for all the components of the vectors until we get to the nth component of the vectors. So sorry, yes, it's like that. And this, so it's just a number because it adds together all the products of the components of the vectors. And if we do this using the same vector, we are just basically doing the theorem, the Pythagorean Theorem, but we are not taking the square root. So we are just doing something like that. If you remember the Pythagorean Theorem, we are just doing which is this, which is the first side squared plus the second side squared, and we take the square root of this and we get the length of the hypotenuse. If we don't take the square root, we're just getting the hypotenuse squared. Sorry. So we are perfectly fine with the length squared of this vector that goes from the center to every point on our window. And why do we need the length of this vector? Because we are just going to use our smooth step function to divide all the vectors in range of our radius, which we chose by taking a number here. All the lengths that are smaller than 0.3 will go to 0, and all that are bigger will go to 1. So if we multiply this by some vector, so we get a color, for example 1.0, 0.8, 0.1. I don't know what color is that, but let's see. If we do this, we get this, a black circle surrounded by this ugly color. What's this? Okay, this is a black circle surrounded by this ugly color, and 0.6. Let's put it the same. 23. All right. So how do we actually get the inner circle? Well, this is really easy. We just have to reverse the result of the smooth step function. So we subtract the result of the function from 1, and we get the opposite. Yes. We get the opposite value. So this can be our sun. We are going to render something like a sun, and this could be our base shape for the sun. And let's see how we can improve that. We can, first of all, we can use our time value. So let's create the clocker object with an argument of 1. Let's divide this by 1000. So we get the second with the floating point values. And let's prepend the u time name. So this is our time value now. This patch is a bit crowded, but that's cool. All right. So let's create the same parameter here in the jit.gl.pix. All right. So we're going to use the u time parameter. First of all, I want to create something like rays of our sun. How we can do that? I guess we can use the cosine function, but first of all I have to introduce you to another function, which is the Arctangent function. This is just the arctangent function, and this is just the inverse of the tangent function. So this Arctangent gives us the angle between some point in a plane and the x-axis. So it's just getting the angle formed by the slope of a line which goes through our zero point through the center. So we're just getting the angle in radians, and we have to give it the point by filling the Arctangent function with the x and the y value of our signal normalized coordinates. So we have to plug the y here in the opposite side of the triangle, and the x in the adjacent side of the triangle. So this is our adjacent, and this is our opposite, and that's the angle. So if we multiply this by some number, let's just multiply the radians. So this is a full, actually it's half period. We get number going from 0 to pi. If we multiply this by 2 and we add this to our length let's see what we get. We get this funny shape. I hope you can see why we're getting this. But the funny thing here is that you can change this number, and you get the number of petals you get is the same of the numbers you put in there. So if we put in the 30 number, we get 30 petals, and it's really fine. It's really nice. Right, let's animate those petals with our time value. We can sum the time value to this angle and see what we get. We get those rolling petals. Alright, I'm not really pleased with those petals yet, because these I want to create the rays of our sun, and these don't really look like rays. So let's take the power of the cosine function. Let's take, for example, the 17 power of the cosine function. Let's see how it looks like. Come on, man. Give me the graph. Alright, here it is. I already did some try. So this is how the cosine function looks like. And if we take the power of this function, for example, the power of 2, we get this. And if we get all the power values, we get also the negative epsilon values. But if we get even numbers, we get all positive values. So let's see what we get with the 17 value. We get those spaced peaks, even positive and negatives. So let's see how we can use this information. If we do just this, see what we get. Yes, we get in the, I want the opposite of that. So I'm just going to subtract this. So yeah, I'm getting those spaced peaks. So these are a little too big. So we need to scale this down by multiplying it with some little value. Maybe 0.02 will do the trick. Let's see. Yes, this is a little small. Let's make this 6. And that's a bit too fast. They're rolling a bit too fast. Let's just divide this by some even little value. Alright, that's fine. Look at the FPS we are getting. These are really high FPS value. Alright. Now this looks pretty cool, but let's see if we can modulate those rays even more. For example, we can take the sine function and sum it with the cosine function. Let's see. For example, we can take another number of rays. So let's do this. We can take another number of rays. For example, let's say we want 18 rays, and let's just do the power. Let's take another power. Let's take the 30 power. So this is all of positive epsilon values for the sine function. And let's see if we sum those, what we get. These are going to be modulated in some way. Of course, we have to scale after we sum them. And yes, we have to scale them, and we get those those rays. Let's, for example, give this another time value, so we get different rounding rays. I mean, let's multiply the time by 1.3 for the sine function and see how it looks like. Oh, easy, man. Hey, it looks like an earth beat. Easy, bro, I just want to do something like that. Yes. So they look more like rays. And what if we modulate... okay, I'm pretty fine with those rays. So let's now add the sky color. What will be the sun without the sky? So let's take a vector for the sky color. Let's make this 0.3, 0.4, 0.9, and let's see how it looks like. If we sum these to the final result, we have the color is overlapping with our sun. We don't want that. So in order to don't have this result, let's mix the sky value with the sun color. So the sky color with the sun color. And if you don't know the mix function, this is just a linear interpolator. So when we have 0, we have the full left inlet. When we have 1, we have the full middle inlet. It's just a linear interpolator. And we have numbers in between 0 and 1, we get all the middle range values. So let's give it the smooth step value. So we actually want the reversed value. So when it is 0, we get the background color, the sky color, and when it is 1, we get the sun color. Let's see if this works. Yes, it works. It works pretty fine. We can also add some sort of aura around our sun, like the rays, the light of the sun aura. Let's do this by creating another circle, always with our smooth step function. So for example, let's do this like that. And let's see, we want always to subtract this result from 1, and we want to multiply this for some value, so we give it a color, like one, a full light. Let's see what we get. And then we need to mix this with our sun color. It's getting a little messy here. Sorry about that. So we have to mix this and this always. We can always base this on our smooth step value. So when it is 0 this time, we get the sun value. When it is 1, we get the smooth step. The aura value. Let's see what it looks like. Yes, the aura is a bit small. And of course, you're not getting the final result because we are mixing it by basing on the we are basing it on this smooth step function. Let's see what we get if we base it on this smooth step function. Yes, we get this sort of aura I was talking about. Let's reduce this component. Yes, no, I don't really like the razor getting really too big here for the aura value, so let's scale them in a different way for the area, for the aura value. So let's take, let's scale these for some different values, so we get smaller arrays for the aura value, like 0.1. Let's see what we get. All right. Yeah, so that's it. What if we want to, just another thing, this is the last thing I want to show you. What if we want to do like gradient for the sky color? Yes, this is totally feasible. It's really simple. We need to mix two colors. You can use this and another one, like guys, this is getting really messy. I didn't want that. So let's take a smaller value, like 0.3, 0.1, 0.1. Let's mix those values based on the normalized coordinates. So a number between 0 and 1, and for the y axis. So we get a vertical gradient based on the y coordinates normalized in range 0, 1. Actually, I would like the darker color to be on the upside. Oh, sorry, this is wrong. On the upside, because this would look like some space color. So we just need to invert those inlets. All right. So if we get this a little brighter. Yep. Yes, something like that. So, guys, I hope this has been useful. We have seen some function here in the jit.gl.pix world, some modulation with sine and cosines, and I hope this was clear enough. And I hope to see you on the next tutorial. Thanks for watching, guys, and see you. Goodbye.